Hi, I'm Kevin Hauser. I'm the author of the brand new unauthorized Ubiquiti Radio and Access Point Handbook. There it is. This is video number 3 in a video series that I'm doing in support of this book. And in this series, I've tried to balance troubleshooting portions with actually, classroom type lessons. So being a full-time instructor, I end up getting a sort of a wider range of questions and concerns, and I'm trying to address these in some of these videos. And today, we're going to look at signals and how they were actually looked at, and we're going to look at radar, we're going to look at DFS. So these are two of the most common questions I get, and it mostly has to do with outdoor radios, but it can also be concerning indoor radios as well. So this particular outdoor radio, somebody will say, hey, what's the optimal signal that I should be receiving on the other side? For indoor, it's the same question. What's the optimal signal that my client should be looking for to be able to modulate or move data at the fastest rate? So this is going to be sort of all together in one happy video here. So the first part, we're actually going to look at signals and how we arrive at understanding what a signal is from a radio. All right. So, and it doesn't matter if it's an indoor radio or an outdoor radio. They look at signals and they look at received signals pretty much the same way. All right. So the first part, we're going to look at decibels and EIRP. So bear with me here. Okay. So the first thing I want to cover, so we have a better understanding of signal strength, is where does it come from? So when you have a radio that's receiving a certain amount of energy or signal from the other radio, part of that is due to the transmit power setting on the other radio. Now, this sounds overly simplified, but it can get a little more complicated. So transmit power, or TX power, is the amount of energy that you're pushing from the radio to the antenna, and akin to volume on a stereo, or that's kind of what it's like, right? The drawback to transmit power is if you have too much transmit power, you can saturate the circuit with too much noise, right? So movement of data, again, creation of data makes noise. So transmit power is half of our equation that we need to understand. The other half is gain. So gain is the ability of an antenna to focus that energy and amplify it in a particular direction. Okay, so gain is a value. Again, it's listed in dBi as opposed to dBm milliwatts. It's decibels isotropic is the measurement. Larger dishes will have a higher dBi value, or a dish that has the ability to focus a wave, kind of like a tactical flashlight you can adjust the beam width on, right? So if you take that super expensive flashlight and you adjust the beam from 70 degrees to 10, the 10-degree beam will go much further. We're not adding power to the flashlight. We're not adding more batteries. We're doing beamforming. Okay, so many of Ubiquiti's products do this, right? So when you buy a long-range access point, or you buy an HD access point, their antennas are doing beamforming. They're actually taking that beam and concentrating it and aiming it in a particular direction to get more gain. All right, so gain is the other half of the equation when we're trying to figure out how much energy should we receive, right? And I'm listing the differences here because they're important. And in a classroom, I want to make sure people have a good, solid understanding of what's going on here. Again, transmit power is one direction only. It's like an amplification of energy. However, the drawback to that is it is only in one direction. Increasing the power on one end will indeed let the other end sense that signal better, but too much can actually make the signal saturated with noise. Gain is reciprocal, meaning that increase of gain on one side of a link will actually make the overall link much better, and both radios will get a better signal. All right, so this is known as reciprocity. When we look at the combination of gain and transmit power, right, this is important to us. And I have a slide here. How do we get more gain out of a link, right? So I haven't included here, on the indoor access points, you could buy an access point with higher gain values on the radios. Outdoors, you'd get a larger dish, or a dish that's more directional to get a better signal overall. So larger dish area gives you more gain. More directional antennas will give you more gain. And the the point here is that the Nano that I'm using is a panel antenna. It doesn't have as much gain capabilities as, say, a light beam. So this is just a overall quick view of how we get more gain. All right, those two things added together, transmit power and gain, equal effective isotropic radiated power. Now, this particular value, or EIRP, is something that the FCC has rules based on this total output power. So the total output power is the amount of power that the radio has, plus the gain of the antenna, minus any loss that there may be between them. Now, the radio I'm going to show you here is a nanostation that does not have pigtail wire, so there is no loss between the radio and the antenna. So our ERP value for this device is fixed. Okay? So I'm actually going to show you that real quick. So let me just minimize this and jump over to my radio. All right. So here in my radio, this is my NanoStation 5. It's not set up to do any link, but we can look right here on the right-hand side. We can see the output power peaks out at 25 dB, and our gain, you can see it's grayed out here, is 13 dBi. Now, the reason this is important, okay, so let's start with why this is grayed out. This is because this antenna for this device is fixed. We cannot use a different antenna for this particular radio. The antenna that it has is fixed, and this is a panel-shaped antenna. So these two numbers added together, 25 plus 13, are indeed 38. All right, so our output power is 38 dBm. All right, so let's go back into the slide here, and I want to explain why that's important. Okay, let's go from current slide here. Boom. All right. All right, so let's look at the ERP value and calculate that to wattage, like how much wattage output do we have, right? So I've actually listed it for you here. The NanoStation AC Loco, the power was 25, the gain was 15. This gives us our 38 dB. Now there is an online calculator, right, that I'm going to show you in a second, that actually converts this to actual watts. Okay, so watts is a measurement of energy. And in the physics portion of my book, I've actually labeled all of the different items that are involved, like watts and hertz and all that stuff. So there's actually definitions in there, right? So here we have a nanostation that can output 6 watts of energy. Now, that doesn't seem like a lot, but it actually is, okay? So if you had line of sight for 50 miles, you could see an 8-watt light bulb. All right, so again, radio waves behave a lot like light waves. You do not necessarily need a huge amount of energy to get a signal. Now, contrast and compare this with a light beam. So our light beam has an output power of 24, gain of 23, which gives us 47. And now we have 47 dB is 50 watts of energy. All right, so the first thing that you might think of is, wait a minute, that doesn't seem to make sense. It doesn't make sense on a regular numeric base 10 numbering system that we all have in our heads. This is a logarithmic value, all right? And I'm going to explain that in a second, but it is a log value, right? To understand what that means, we need to look at the rule of 3s and 10s. Now, this is for the output power, or the ERP power of the radio, right? So if we have a radio that's ERP value is 3 dB more than another radio, then you're getting twice as much energy out of that radio. If it's 3 less, then we're getting half as much energy. Again, we're looking at ratios, right? We're looking at raw ratios here. An increase of 10 is 10 times stronger, or it could be 10 times weaker. So at the bottom, we see a value of 47 is twice the strength of a value of 44. This is in our ERP value, right? Where 57 dB would be 10 times stronger than that value of 47. Right, so one of the things that happens in the world of outdoor radios is that you'll see larger radios with lots of output power and lots of gain, and they can actually, push signals a long, long way because of the ability of this output power, right? So for our standards, for our purposes, the FCC again puts limits based on channels and frequency that we actually use in the unlicensed band. All right, so what I'm going to show you is I'm going to just open a website here real briefly, and I'm going to show you what we have here. So this is a everything RF calculator, right? So again, I'm going to show you the rule of 3s and 10s here. Okay, so let's go to that value that we had before, the 38, right? Decibel in milliwatts. So we'll click calculate, and we can see that we have 6 watts of energy. All right. So for our 47 dBm, there's our 50 watts. Now again, I said that an increase or decrease of 3 dB will actually double the amount of energy, and the energy is at the bottom. So let's see if I'm right. So we'll change this dB from 47 to 50, and that should change to about 100 watts at the bottom. There we go. There's 100 watts. If we move this up to 60, this is our 10 value. We've increased by 10. That should be close to 1,000, and it is right on the money. All right, so this is a logarithmic, a base 10, right? This is a log 10 system that actually is converting this. The reason we have to do this, the reason we have to understand decibel in milliwatts, is because the amount of energy that leaves the radio is not always measurable the same way as the amount that we get at the other end. All right, so what do I mean by that? To understand that, I have this terrible slide. Let me go down to it. I created this slide, and I just sort of made this real quick in Paint, and I use this in class all the time. So what we're seeing here is we can see our orange representation of our noise floor that we saw the other day. And we can see we have a light beam AC up there that's spitting out 50 watts of energy. Now, if you convert that 50 watts into milliwatts, it's 50,000 milliwatts, which sounds like a lot, which it is. Now, that light beam is talking to a receiving station, right, that's distant. And for this demonstration, we don't really care how distant it is. So this is showing that our received signal that we're getting at that station is -50. But when you put -50 in the calculator, you're going to end up with this tiny little milliwatt number of 0.00001 milliwatts, a very, very tiny amount. But because it is 50 dB off the noise floor, right, it's considered an optimal signal. Right? So again, the rule of 3s and 10s apply here as well, but it has to do with how far off the floor or how far off the noise floor we are. Obviously, if we're further away from the noise floor, we're closer to the sending power. We're closer, right? So in this case, -40 would be a stronger signal. -30 would be an extremely strong signal. -80 would be a terrible signal. One of the things I tell my students is that we don't want to have an outdoor radio that's operating too close to the noise floor, because at times that radio will have trouble understanding signal versus noise. He may not be able to tell the difference. So if your noise floor is -100, quick and dirty, and your signal is -50, that is an optimal signal. All right. So -47 would be twice as much signal. -40 would be 10 times as much signal. I remember a installation that we had in rural Texas, and the installer ended up hanging a client radio, and he wasn't really super familiar with dB and receives energy. He was obviously just trying to get the best signal. And I said, well, what signal did you end up receiving? He said, well, I got a -76. So I said, well, how much worse is that than a -50? And in his mind, it's 26 worse. Makes perfect sense. 76 minus 50 is 26. That's not that big of a deal. However, if we look at the rule of 3s and 10s, how much worse is -76 than -50? Again, for every 10, it's times 10. So from -50 to -60, it's 10 times worse. From -60 to -70, it's 100 times worse. From -70 to 73, now it's 200 times worse because it's double. And from 73 to 76, it's 400 times worse. So we're looking at ratios. We're looking at the difference between sending and receiving as a ratio, not necessarily in milliwatts, but as a ratio. And I think that's some of the hardest things for people to really wrap their head around, because we're sending lots of energy and we're only getting a little piece of that pie, but we're getting enough of it to understand what that signal actually is and what that data actually is. All right. So again, luckily for us, these radios are super, super sensitive and they can actually see this, and that's a good thing. All right. So optimal signal, right? So again, for outdoor radios, and this is just back of the matchbook, it's not always going to be the same noise floor. -50 is obviously optimal, but that doesn't mean that that's what you have to strive to get. It's just what would be perfect for that noise floor. Okay? Now, industry standards will say that you probably don't want to have a radio that's within 20 dB of the noise floor. In other words, if the noise floor is 100 or -100, you don't want to have a signal of -80. That's a little bit too close to the floor. Okay? Now, also for outdoor radios that are line of sight or point to point, you don't want too much signal to actually damage the radio. So Ubiquiti recommends that at -40, you may want to turn the power down. Right? That may be too much signal. Now, for indoors, it's not quite the same problem, but for outdoors, it can be. Now, this is a representation I pulled off of Wikipedia somewhere. This is our 5 gigahertz spectrum. All right, so many of us are familiar with 2.4 in unlicensed spectrum and 5 gigahertz. Now, the difference is vast. In 2.4, we only have 80 megahertz of total spectrum from the bottom all the way up to the top. And in 5 gigahertz, we have 580 megahertz of spectrum. We have tons of room here, right? So we can have 24 non-reused 20 megahertz channels in 5 gigahertz, which is awesome. All right, so the second part of the troubleshooting, or the second part I want to talk about, is the user or the installer says, I'm getting an error on my radio that says radar detected, right? Why am I getting this error? Is that bad? And it shows up in red, so yes, it's bad. Now, in the two center portions of this 5 gigahertz channels, we see the Uni 2 and the Uni 2 extended. Okay, so the Uni stands for Unlicensed National Information Infrastructure, which is fancy terms that the FCC uses. So in the Uni 2 and Uni 2 extended, one of the rules is that the radios have to be what's called DFS compliant, or Dynamic Frequency Selection compliant. There are forms of interference that our outdoor radios can sense. Okay, and these would be things like Doppler weather radar, marine radar, air traffic control for military. A lot of these other devices use high-powered radios, and they sometimes extend into one of these two areas. Should that happen, your outdoor radio will not want to share that frequency or that channel because it can actually be damaged. So when we use an outdoor radio, this is a broadband, low-power radio. It has lots of channels. You can see this 20 megahertz wide channel at the top, that it has a center channel and 19 subcarriers. And if it's using OFDM, it has 39 subcarriers. Well, these are low power, as opposed to something like a Doppler weather radar, which is very high power and is called narrowband because it only uses one channel and one frequency. All right, so the difference is vast. An outdoor radio that senses one of these forms of interference, right, is going to have a problem. So here's the definition, DFS. Frequencies in these two ranges are subject to guidelines published by the FCC. Now, if you can't sleep, I recommend reading up on these guidelines. Sources of these signatures. Again, they're listed here, right? Now, I've had students tell me, listen, I am nowhere near a weather radar. I'm nowhere near the airport where they generally have these things. I'm nowhere near any military base. Why am I getting this? Why am I getting this signature? Well, if we look at the bottom, high energy directional waves with line of sight can cause this problem. Your radio is a half duplex device. It has send cycles and receive cycles. During its receive cycle, if it detects energy that is not destined or not actually identified as coming from its other side of the link, and it's high enough energy, that can indeed generate this sort of radar signature, right? So if somebody had a very high powered radio aimed directly at you, this can actually cause your radio to think that this is a DFS event. What's the solution for that? Well, the initial solution is pick another frequency or another channel that may not be subject to this radar signature. That's the initial solution. You may not always see this in a site survey. You may see this as background noise. If you're running AirView, you might see some background noise, and that could be what this radar signature actually is. Is it really radar? Well, not always. Again, outdoor radios are generally more likely to have this problem because this is only in the 5 gigahertz range, right? So indoor radios that are running 5 gigahertz are generally considerably lower power, and they don't like to go, 5 gigahertz does not like to go through objects like walls and windows and trees. So outdoor radios are more likely to have this issue. And again, a radio with direct line of sight and high power can actually trick your radio into thinking it is actually a radar signature. For an indoor radio to have this error, it's highly unusual, okay? But it can happen. It actually can happen. So I know that's a lot of information to cover, and that's why I kind of wanted to break it into pieces a little bit. I've seen this question many times, like in a classroom environment where people are trying to look for an optimal signal. Now, right in Unify, you can actually go to the client menu. You can actually see what kind of signal a client's getting. Now, one of the things you may be asking yourself at this point is like, can this client, like this tiny phone, receive too much energy? And the answer is probably not, right? The antennas on this are not directional, and they're not super sensitive to that they could be damaged by too much energy off of an access point. However, outdoor radios can be susceptible to this. So what are we looking for indoors? I can honestly say that if you were to use a tool like Insider by MetaGeek, you would actually see the quality of signal level. Once you get to like negative 80, 82, 83, it's pretty bad. Your device will not really have an easy time understanding noise from signal. And this is why I recommended in the prior video to actually limit that number using minimum RSSI in the radio. We don't want this little guy walking around too far outside of the cell range and now get a really poor signal, okay? So optimal, right, is going to be better than negative 80. Too much would be indoors would not be such an issue as it is outdoors, again. So as long as you're far enough away from the noise floor, the clients will be able to understand that signal. As far as point-to-point radios outdoor, it's much more finite. So be aware of that. Indoors, we are point-to-multipoint. We have lots of clients. We have lots of reflection. We have lots of multipath. So we can kind of get away with higher signal levels. Be aware of that. Again, there's rules. If you're a wireless person, you should read up on these rules, on the FCC rules. You should understand how much power level that you're allowed to have on an outdoor radio. It's very important to understand that. So when you see those Uni 1 and 2 and 3 sections, each one actually has, by regulation, allowed to output a certain amount of energy for its devices. It would be a bad idea to get a radio, okay, and set it to a country code that allowed for more energy. That's a violation of the FCC rules. You don't want to do that, okay? Sorry, I opened that, made noise. So Ubiquiti sells world radios, and they sell U.S. Radios that can be set to Canada, Puerto Rico, or U.S. So in the U.S., you don't want to deploy, and I mentioned this in my book, you do not want to deploy a world radio, right, in the U.S., right, and set it to some country code that you think, well, I'm not going to have a DFS problem if I set this country code to Afghanistan or something. You don't want to do that. That's a violation of the SEC rules, okay? So I hope this has answered some questions about the radar and about optimal signals. In a future video, which is exciting for me, we are going to talk about the future of wireless, like Wi-Fi 6 and 60 gigahertz stuff. We're going to talk about that sort of future and how that's going to solve some of our current problems in our current environment. Thanks for watching. I really appreciate it.